If you see, this is our first slide that you know very well because it's our IADF school. It's the second year that I organize this school in Benevento, and it's thanks to you because it was a success last year, thanks to the participants. And this year, let's cross the fingers. It's up to you, to me, to all the organizers, but let's hope that everything will work as we hope. As you can see, there are a lot of sponsors, GRSS, IEEE, but also other ones, the European Space Agency, Thales Alenia Space, Cosine, Intelligentsia, Strega Alberti. Strega means witch. I don't know if you know. There is, the ugly woman like me flying on the broom. Strega, do you know? Okay. And the Strega Alberti is one of the best company in Benevento. They produce some sweets, but also a very famous yellow liquor, very good. It's not allowed to drink in these days, but then you can buy and you can bring back with you. And Strega Alberti will give us some gadget. Confindustria, University of Benevento, that besides the venue, gave us also a sponsorship. Cosmind, and I want to thank SMS Engineering because he's here. He's the only sponsor here. Just 1 second. Yeah, a big clap to him. He was the only one to come today. He brought me a small dog that is there, Massimiliano. A funny dog that he told me that this dog went in the space. I don't know if it's true, but it's nice to believe, Okay, so this is a gift for me. Okay, so thanks to all the sponsors, thanks above all to my university, that is allowing all of this. Okay, next slide. So this presentation is about quantum computing. Why? Quantum computing is not, a recent topic, but what we did with my group, where Alessandro is one of the leaders of this group, not me, but him, was to think some years ago that quantum computing could be transferred with the quantum machine learning, with the quantum artificial intelligence, to Earth observation, to remote sensing. This was the idea, and when we started, just 3 papers in the world were doing something similar, quantum machine learning applied to remote sensing. We started with this small group. We involved some people from the MIT, not just because the MIT, Massachusetts Institute of Technology, is MIT, but because my university has an agreement, and every January we invited and we host students from MIT. We arrive until now to almost 100 students from MIT. So that year we had the idea with Alessandro to involve some students and to work with them. Our group in this moment is composed by Francesco Mauro, that is here on the first row. He's doing the PhD with me, with Alessandro in the European Space Agency. There is Alessandro, Maria Pia Del Rosso. She finished the PhD with me, and she's working with a company right now, MBDA, I think that we can say. And that myself, Bertrand Lesseau, he was in the PhilLab, now he changed his affiliation. And we have the honor also, for me, for all of us, is an honor to have a Professor Paolo Gamba in our group. Is from the University of Pavia, and in the GRSS, everybody knows him. Okay, next slide. So, what is the motivation about this summary? To do some quantum computing basic, something about the hybrid quantum classical neural networks, why machine learning for Earth observation, some use cases where I will ask Alessandro to help, and some conclusions. We can go ahead. It's a little bit complicated for me to look in the camera, to look here. Where can I put a position to read the slide? Otherwise, it's better to stay here. You're right. I don't remember the slides by memory. Okay. So, the motivations. The Earth observation is at full speed in this moment, in space and on ground. That means newer and newer satellites. And this means a lot of data, what is called big data, almost 150 terabytes every day. So the classical computers are not able, they reach their limit, are not able, to elaborate and to process this data. And this is where quantum computers came to help. So quantum computers are there somewhere, but obviously, there are some companies working on these quantum computers. I will go faster. So this quantum computing or quantum technology race, it's something very important because a lot of countries are working on this. It's a kind, I would say, of a peaceful war. I don't know if you like, this way to say, but the United States, Japan, China, Russia are all trying to succeed in the realization of the quantum computer. Because imagine the country that will be able to have the faster and the biggest quantum computer will be there, will be the strongest one. We have a scenario with some countries, as I said before, but also some big companies like Google, IBM, Microsoft, Honeywell, and many others that are less famous but are working hard to stay, in this competition. What is the point? Is that we are moving from microprocessors, that is, the common unit inside the normal computer, to quantum computing chips, that are something completely different, because the quantum computing chips rely on quantum mechanics, so something related to the basic atoms of the material, of the matter. So the quantum physics, the quantum mathematics are all topics very complicated. It's not the normal mathematics, but something that goes beyond what we usually study and utilize. So what are the outcomes that the quantum computing is bringing, or at least, the objectives? Is the speeding up and optimizing certain computation processes, leveraging the probabilities nature of quantum phenomena, and the advantages is the ability to solve classically intractable problems, and the use of quantum devices as in a variety of fields, including machine learning and Earth observation. There are also some limitations, so nothing is completely positive. The limitations are related to the fact that quantum computation is still in a fairly developmental stage. There is this noisy intermediate scale, because quantum computers are prone to errors, is what is called the NISQ era. And the quantum computers need to be kept ultra cold. They cannot stay in a normal room. And so these are all, challenges to be solved. About the outline on quantum computing is, it would require more time, and we, unfortunately, we went a little bit ahead, so I will be fast on this. What I want to say is just that the normal bit assumes two values, as everybody knows, 0 and 1. Instead, the unit that we use in quantum computing is called a qubit, and it can assume in a probabilistic way a value that belongs to a combination between 0 and 1, with the law of probability that is expressed with this equation. What is usually used is this what is called the block sphere that you see on the right, on the bottom of this slide. So each point in this block sphere represents a possible values. Is a possible value because it's a probability So it's a likely value, but when the measurements is done, is achieved, the qubit collapses to the values 0 or 1. So it comes back to the normal nature of a bit. And this obviously seems something like, full of fantasy, a little bit difficult to, to follow, but is the way in which the quantum computers work. I skip some slides. I want to go to the basic keywords in quantum computing that are the qubit that I just present. The superposition is what I said before. So it's this capacity to stay in two states contemporarily. And this is the biggest basic situation in which the qubit can stay. And another thing that is a key word, but a situation of quantum computing, is the entanglement. I explain entanglement in my way, that is Silvia's way. That means that, what is entanglement? You have a qubits, and these qubits are somewhere. When you put these qubits close each other, they learn how to know, maybe to love. Do you like if I use this word? To like, let's say, to like each other, and they become entangled. Even if you put them apart, very far away, what happens is that when you measure one qubit, the same measure, the same output is given by the other qubit, even if they are far away, because they were entangled in a certain moment, and they remain in these situations. I always express entanglement like the empathy, the feeling between people. They become entangled, they have the same, the same feelings about something, even if they are, far away. This is the way in which the qubits work, but I just say that there are several circuits that are called quantum circuits, and there are several names, Hadamard, Pauli, and so on. And these quantum circuits are used inside the models to realize these different architectures. These are some examples of the block sphere. Sorry. And this is the part in which quantum machine learning met the Earth observation, creating the quantum machine learning for Earth observation. There are different schemes, what are called the late hybrid scheme, when in a classical model, the last part becomes a quantum layer, or a fully quantum scheme, or an early hybrid scheme, when the quantum part in a general classical model substitutes, let's say, the first layers of the architecture of the model. From here ahead, I would like that Alessandro comes to help me, please, and he's going to present some of the work that we have done with him, with Francesco, and with our group. We have made some publications. Some are already published. We have a transaction. Let's cross the fingers, because for all of us, to publish on our journal transaction for geoscience and remote sensing is quite difficult. So we have a transaction that passes the first step, and we are waiting for the final results. Let's see. And Alessandro is going to present part of our work. So thank you.
I'm back. Okay, so let's start from the left side here. I hope you see no, you don't see let's use this one. Okay, let's start from here. So I will ask you a small question. What do you think this scheme belongs to? It's early, fully, or late? Who's going to reply? Okay, I'll help you. So it's late scheme, because if you, maybe the image is quite small, but if you see, the quantum part is at the end of this network. So we started with this study. It's our pilot study It's the first work we produced 4 years ago, 3 years ago, I don't remember. Some years ago. 4 years ago, okay. And we started by applying some hybridization to a really famous neural network in the field. That's a LeNet5 network used to classify Earth observation images. So as you can see, we have a first part of classical AI, classical deep learning, essentially, that is extracting information from the images. Then we have this quantum block, the blue one, that is applying some quantum computation to this compressed data and returning the actual prediction. So from this, we started to exploring even more application. Francesco is leading this on the quantum graph neural networks. So we are trying to, put some quantum components inside the graph neural network that are well known to capture global, especially in Earth observation, global information at global scale, correlate information at global scale. But also we are trying to do some, let me call it quantum image processing application. In this case was used to filter some speckled noise from SAR images. And finally, we also have some, I will call it more fundamental research that is about hyperparameter tuning in quantum neural networks. I don't know if in the slides we have, yeah, okay, because Silvia prepared these slides. So this is more or less a summary of what already said. We have this paper published about this classifier in Earth observation. In collaboration with MIT, so that's the project that Silvia was mentioning at the beginning, in collaboration with the MIT guy, and also with some colleagues from Sapienza. So we used, in this case, a very famous data set in the field that is the Eurosat. I guess all of you probably knows it. And it's a data set of Sentinel-2 images divided in 10 classes. And the scope of this project was to demonstrate that quantum computing can bring some benefit to this field. So this is a picture of the data set. We had 27,000 labeled images divided in 10 classes. As I said, Sentinel-2. You can find it on this page and download it for free. This is the adaptation we did to the network. So we have 3 convolutional layers, a flattened layer, then a fully connector to adapt the input of the convolutional part to the quantum circuit, and then at the end we have another adaptation layer to adapt the output of the quantum circuit to the final prediction. I'll try to go quick on this because I think we have too many slides. But essentially a way of putting these hybrid models together is through the circuits that Silvia already presented to you. So a circuit is a way of programming your quantum computer, nothing more. And a circuit is composed of several gates. As you can see, Silvia presented Hadamard and rotational gates and so on. And one way of connecting the two is via this variational parameterized quantum circuit. So essentially, you have this rotational gate. You can imagine that this rotational gate applies a rotation to the qubit position in the Bloch sphere, essentially. And this is this rotation depends on the output of the classical part, essentially. Then you have more gates that are tuned during the training phase, but let's say the encoding is done via some rotational gates and the tuning is done via the others. So some results here. We tested several circuits and we found out that the real amplitude circuit was the best candidate for this application. Actually, at this, I mean, it's true still, right now it's still true, this information. So there is no way a priori of deciding if a circuit is the best for a specific case. I mean, we don't have any tools. So you have to test several configurations, essentially. And yeah, as you can see, I mean, probably not really, but if you know about the confusion matrix, you should have ones along this diagonal. And in this case, blue, a dark blue represents a number close by 1. So if you see the real amplitude is the one that outperforms the others. Okay, I think I can skip this one for now. So if you like, maybe not today, but when you go back, you can try this tutorial. It should be still functioning. You can run it on Google Colab. So I mean, it's an easy way of entering this field, I would say. And it is based on this library. I will give you more details in my presentation later. So the other use case is about the SARD speckling. Okay, sorry if I jump between slides, but it's not my presentation. We also had a paper on this, and the idea of this paper with this application was to filter some noise from SAR images. I guess the ones that works on SAR images knows about speckle. Actually, this project was a spin-off of another project we ran a few years ago during my PhD, and it was about the use of AI, classical AI, to remove speckle. And then in this case, we applied a bit of quantum. So we started from this new way of doing the convolution. So you know that classically now deep learning is using a lot this convolution to process images. And we try to develop a convolutional neural network, so a quantum convolution implementation of these networks. So I will not give you all the details, but essentially you have, as for the classical convolution, you have a kernel. In this case, the kernel is represented by a quantum circuit. So this kernel is moving through your image, extracting information in a different way with respect to the classical network. And yeah, essentially, we replaced some layers of the classical network, extracting information with the convolution and applying the same architecture proposed in the original paper. We saw some improvements using this new speckle filter. Okay, use case 3, it's about the quantum graph neural network, and in this case, we applied it to study, to forecast, let's say, the evolution of the El Nino. So I don't know if you know about it, but let's say it is it's described here. It's an abnormal warming of the central and eastern tropical Pacific Ocean, and is causing a lot of climate problems also in Europe. Actually, I think we had it this year, if I'm not wrong. Yeah, also in this case, we have a paper in IGRS this year, or last year, Francesco? This year, okay. Sorry, my memory is really bad. We are also trying to go ahead with a new paper, but essentially what we did here is like a pilot study. So graph neural networks are already quite complicated for the ones that knows about those. And we try to start to put some quantum in it. And maybe in my presentation I will give you some details about why we use quantum and which are the benefits. So we started from a dataset published in the State of the Art. You should find all the details in the paper if they are not here, I guess. Yeah. So it's a collection of several information from several satellites developed by ESA and also NASA in this case. Okay, the method is quite easy to understand because we replaced, in this case, it's a late scheme because we replaced the final part of the graph neural network with some quantum components. Essentially, we used a quantum MLP, multi-layer perceptron layer. Also in this case, we tested several circuits, and we found one candidate that is the best one. So in this case, you see another important information that we are trying to, let's say, introduce in our research. It's about the hyperparameter tuning. Maybe this part is at the end, but I can explain it right now. So as you see, the circuit is composed of a few lines. Each line is representing a qubit essentially. So, and there are some gates that are applied to a single qubit, and there are other gates that are applied to multiple qubits. For example, to get the entanglement, you can apply the CNOT gate that is putting together two qubits. Plus, there is another information. Maybe it's better if I go back to some circuit here. No, yeah, here as well. So you can have layers inside of this structure. It means that you can have, for example, repetition of the same gates every. I mean, it depends on the number of layers you want to add. And this is another important parameter because it also, as for classical AI, it gives you more power if you add more layers. So it's important to tune these parameters because maybe in this case it's not easy to understand, but in some cases you can have, I mean here for example, you can have some configuration with less amount of qubits and less amount of layers or vice versa, having the same accuracy. And this is important because you can save some resources. So why I say this? Because there are quantum computers outside. They are still in development, as Silvia said at the beginning. And to have access to them, it's quite trivial. So if you can save some resources, it's always better. Okay, in these two graphs, essentially, we are showing some interpolation between all the experiments we did with various configuration, and we found let's say I would say the most economic one and the better performing. Okay, sorry if I go fast. We have another presentation.
Yeah,
okay.
I'd like also, before the other, there is an online session. Before that, I'd like to listen from them.
Okay.
And we have all these researchers, and we want to listen also from you and see. So be prepared to ask questions and to interact with us.
Okay. Yeah, because I also have another small presentation, if I may. Yeah. Okay. Okay. So. Yeah, the online presentation. Okay, okay. Okay, so I will not repeat again this concept because I just explained to you what is a quantum parameter selection in, let's say, quite in a fast way, but you can find details in this paper. So this is strictly about hyperparameter tuning. Let's see if I have a graph to give you an idea. Okay, so that's what we did. We have this basic implementation of a quantum circuit with some layer gates to encode the information. Then we have these layers that are repeated several times. So for now, we started from, let's say, a brute force approach. So essentially, we sampled the space of configuration in a certain way, in a kind of symmetric way, I would say. And we ran an experiment for this configuration, and we try to understand which one is the more efficient in terms of some metrics that we identified. But I mean, in the future, we aim to have some automatic tools, like if you're familiar with Optuna, that's quite a well-known tool for deep learning to optimize your network. Okay, I think we can close for this and jump to mine because, I mean, this is the presentation from Silvia. I think you have her email, but if you want to take a picture of this, also to connect via LinkedIn, I will jump to the other then.